Section 9.8 talks about exceptions to the octet rule, and where we're going to start with this is what I'm going to call an incomplete octet. It turns out that atoms with fewer than 4, meaning 1, 2, or 3 valence electrons, are often more stable with less than 8, less than an octet. So let's look at the example of beryllium dibromide. Now for BeBr2, beryllium has, when it's a plain atom, 2 valence electrons, and bromine has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So because beryllium is a metal and bromine is a nonmetal, typically you would expect those electrons to be exchanged. Thus, you would have Be, which lost 2 electrons, is now 2+, and the bromines would have each gained an electron and would be negative. And if you were not given a table of electronegativities, you would say metal, nonmetal, ionic. But actually, if you look at the electronegativity values, the electronegativity of bromine is 2.8. The electronegativity of beryllium is 1.5. So the difference there is a difference of 1.3. Your textbook says that it's only ionic if the difference is 2.0 or greater. If it's less than 2, it's going to be covalent. In this case, polar covalent, but shared nonetheless. On a test, if you weren't given electronegativities, you would say ionic, like this. If you were given them, you'd be expected to look at the difference, and you would go covalent. So if it was covalent, we might follow the steps in your book of how to draw Lewis structures for molecules, molecular compounds, covalent compounds. And it says first determine which element is in the middle in your skeleton, and we'd expect the less electronegative beryllium to be in the middle, and the bromines to be our outer terminal atoms. Step 2, we add up all the valence electrons. Beryllium comes in with 2, and each bromine comes in with 7. So the whole molecule has 16 to work with. Immediately, you should see that when this has 2 right here, that's fewer than 4, and that should be an alarm that maybe this is going to be okay with less than an octet. So we move on to the next steps. Give everybody single bonds. That uses up 2, 4. Now we have 12 left. Then add lone pairs. The book recommends that you add them to the terminal atoms first. This bromine has 2 that it's sharing, so it needs 1, 2, 3, 4, 5, 6 more to have 8. The other bromine also, since it's sharing 2, needs 1, 2, 3, 4, 5, 6 to have 8. And now we're out of electrons, but beryllium does not have an octet. Excuse me. So one way to deal with this would be to take more from the bromines and share. For example, if this bromine drops some in and this bromine drops some in, we could have something that looks like this. And this satisfies the octet rule for all atoms. So octets satisfied. Whereas here, Be has less than an octet. But it turns out this structure is better. This one is more stable. Why is it more stable? It turns out if we calculate the formal charges on each atom, the formal charges are going to be better. In the top structure, if we calculate formal charges, there's 0 for every atom. 0, 0, 0. And 0 is the best. In the bottom structure, it would be +1 for bromine, -2 for beryllium, and +1 for bromine. Those are larger formal charges. That's bad or unstable. So both are valid resonance forms, but if it asks you for the best one, you want the one that has 0 formal charges, 0, 0, 0. Keep in mind that all these numbers still sum to the same net charge. BeBr2 has a net charge of 0 because there's no number written in the top right-hand corner. 0, 0, and 0 add up to 0. +1, -2, and +1 add up to 0. But these are distributed better where they're all zeros individually. Another way to not obey the octet rule is what we call an expanded octet. And that's atoms that have a valence shell of 3 or greater, so n equals 3 or greater, can expand beyond 8. They can have more than an octet. So here, we're going to look at PO4 with a 3- charge. You might remember that this is called the phosphate polyatomic ion. And if we were going to draw the Lewis structure of this, the phosphorus is the least electronegative, so you can imagine that the phosphorus is going to be in the middle, and the oxygens are going to surround it. If we add up all of our valence electrons, phosphorus would have 5, the 4 oxygens would each have 6, and then with a -3 charge, that has 3 extra electrons. That adds up to 32 valence electrons total. So we make single bonds, 2, 4, 6, 8. That gives us 24 left. Each oxygen is sharing 2, so it needs 1, 2, 3, 4, 5, 6 more for an octet. That leaves us with 18. The other oxygens each need 6 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That uses up all of our electrons, and most often we might stop here and say, okay, everybody has an octet, we're good to go. But if you were to calculate the formal charges on each of these atoms, and for practice, I would encourage you to do that both for this structure and for the BeBr2 previously, each oxygen is -1 if you calculate the formal charges. And the phosphorus is +1 if you calculate the formal charges. Notice how 4 negatives and 1 positive give you your net -3 charge. None of these are 0. So this is not the best way to do it. If nobody could expand beyond an octet, then we'd have to stop here. But if one of them has n equals 3 or greater valence shell, it can have more than 8. And if we look at phosphorus in the periodic table, it's in the 3rd row. So its valence shell is n equals 3. That means it can have more than 8 if it could help. If it's positive, it would love to get some more negatives. Who could it get some more negatives from? It could get some more negatives from one of the oxygens. So if one of the oxygens kicked down a lone pair to make a double bond, this molecule would look something like this, these are two different resonance forms. And now that this double bond has happened, the phosphorus has more than 8. It has 2, 4, 6, 8, 10. But it can do that because it's in the third valence shell, and anything in the third or beyond can do that. And if we do it, that means that now these oxygens are still -1, but the phosphorus is 0 and the oxygen is 0. Again, I strongly encourage you to calculate these formal charges on your own, but since this one has lower formal charges, it is more stable. So if they ask you for what's the best resonance form, this one would be better because it has lower formal charges, more are close to 0 or zeros. You might wonder, why is the third valence shell so special? Well, let's take a look at that. In the first shell, n equals 1, all we have is the 1s orbital, which can fit a maximum of 2 electrons. In the second shell, we have the 2s and 3 different 2p orbitals, so we can fit 1, 2, 3, 4, 5, 6, 7, 8 electrons maximum. That's where we get the octet. But in the third shell, remember, if n is 3, L can be 0, L can be 1, or L can be all the way up to 2. Remember, the maximum is n minus 1. So we get the 3s, the 3p, and we get the 3d subshell. And there are 5 orbitals in there. So not only can we fit 1, 2, 3, 4, 5, 6, 7, 8 in the 3s and the 3p, but we've got more room, more pockets, more places to put orbitals. They're not always used, but they're still there to put more than 8 if you need to have more than 8. So I've cleaned up a little bit of space here. If we look at the first shell, all we have is the 1s, which you might remember can only fit 2 electrons maximum. In the second shell, we have the 2s and 3 different 2p orbitals. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons maximum. But if you move to the third shell, we have the 3s, the 3p, and even though it's not always used, we have the 3d subshell. So not only can we fit 8 in the 3s and the 3p, we can fit more than 8 because we have this extra space to throw extras in if there's some advantage in doing so.